Alright, so this is going to be a slightly split video. I want to work on, well, work, and just to help on conservation of energy problems. So the objectives for this video are know what work is and how to solve for it, and then know how to solve some more difficult conservation of energy problems, so we have some practice on those. Alright, so to start with work, which we denote by a W, nice and simple, is a mechanical energy transfer. You can think of it as the ability to do work is equal to energy. So energy is just the ability to do some work. Alright, you need energy to do work, same thing in physics. The formula for this is W is equal to FD, where, or if it gets more complex, which we won't get too complex, but in case, this is where F is force in newtons, and D is distance. How far have we actually gone? And this is in meters. So, and this is a modifies, so if it's at an angle. So if you're doing work, it essentially must be in direction of the force. So what I mean by that is if you're pushing something down, you're not doing any work because it's not going anywhere. So to better illustrate that, for example, say we have a box and we are pushing it so that it moves 5 meters to the right. However, we're actually also pushing it up with 20 newtons. All of those 20 newtons do not go into it. Only the newtons, we'd have to break it up, only the newtons going in this direction would count towards solving. So it has to be only directly in the direction of the force. You can't push up and then count that as helping push it to the right. If you're moving it to the right, force must also be to the right. If you're moving it up, force must only be counted from the up force. So we will have to occasionally break these apart. Alright, so read through the problem, you can draw a picture, and then try to solve using the formula from the previous notes. Alright, so in this problem, we have a car. It doesn't even matter how heavy it is, because we know how much force he can push it with. So our force is 108 newtons. The distance, and this is all horizontal, because he is pushing it horizontally, unless he wants to push it up for some reason, but that would be a waste of energy. He has to push it 218 meters, and we know that work is equal to the force times the distance. That's in the same direction. These are both going horizontally, so they can be exactly equal. So work would just be 108 newtons times 218 meters. Plug that into your calculator and you'll get 23,544. And this gives you Newton meters. However, a Newton meter is a joule. That's the definition of a joule. So it's 23,544 joules. Alright, so next is conservation of energy. When you're solving a conservation of energy problem, first, read it. 2, draw a before and after picture. And then 3, write out your types of energies for before and after. And then 4, find variables. And 5, use equations and solve. So we'll write this down, and then we'll do a practice one, and I'll give you one to try on your own. Alright, so it's the conservation of energy. A 10 kilogram book falls from a height of 50 meters. How fast is it going 10 meters from the ground? So you always want to make a before and after picture. So we have our book, and it is falling. So I'm assuming it is 50 meters up here, and it's a 10 kilogram book. Next, we're looking at it right before it hits the ground at 10 meters. It is still 10 kilograms. So when you're doing this, we know that the energy at the beginning is equal to the energy at the end. So now we need to talk about what types of energy. In the beginning, it's not falling yet, it is starting to fall. So the only type of energy here is potential. So we have gravitational potential energy here. At the end, it's still above ground, so there is a little bit, this is the initial, there's still a little bit of gravitational potential energy, but it is also falling, so now there is kinetic energy. From here, now that we know what's happening, our types of energy, we now essentially built our equation, so now we can just plug in. We know that it would be the mass times gravity times the initial height is equal to the mass times gravity times the new height. This is this one, so let's color code here. And then plus our kinetic energy, which is 1/2 mv squared. Our ultimate goal is just to figure out this, and we actually know everything else. We know our mass. Notice, mass is in each one of these things. We can actually just get rid of it. So our new equation reads as our gravity times our initial height is equal to gravity times our new height plus 1/2 v squared. At this point, we can start adding our numbers. Gravity, I'm going to use 10 for simplicity's sake, 10 meters per second squared. Its original height is 50. Gravity has not changed in this time. Its new height is 10. And then we're adding it to 1/2 v squared. We do not know v yet. So this is 500 is equal to 10 times 10 is 800 plus 1/2 v squared. Move this over. So we get 400 is equal to 1/2 v squared. Multiply by 2 on both sides, which will give us, need more room, that will be 800 is equal to v squared. Square both sides, that gives us v is equal to 28 meters per second. Alright, and then I'm going to give you one to try it on your own, and then I will help you with it. Alright, so read through the problem, and then I'll go over it. Remember, for both A and B, give yourself a before and after picture to make sense of it. Alright, so a kid is given a push down a hill that from a starting height of 10 meters. What I want to know is how fast is she going at the bottom of this hill? So, to do this, we need to write out what are my before and afters. So, energy before, energy after. So, before, she's moving, so she has both some initial kinetic and some initial potential. And at the end, she's at the bottom, so she only has kinetic. We can now plug in our formulas, which would be 1/2 mv initial squared plus our mgh is equal to our new 1/2 mv, not initial, squared. Notice m is in all of these, so you can get rid of it. So then you go to 1/2 your initial velocity, that was 6, plus m is gone, remember, gravity, so 10 times the height, also 10, is equal to 1/2 v squared. Do the math on this. This is 18 plus 100 is equal to 1/2 v squared. That gives us 118 is equal to 1/2 v squared. Multiply both sides by 2. You get 360 is equal to v squared. And then if you square root this, v is equal to 18.97. So this is your final velocity. You should probably keep that so that you can do part B. Alright, then, new one, she's at the bottom, going very fast. We now want to figure out how high is she going to go. Everything is still the same, but now we know if we figure out energy, types of energy before and types of energy after. Beginning at the very bottom, we said she's only got kinetic, and at this one, when she's at the very as high as she can go, and she'll stop and then start going down. The only type is potential. So again, now you can put in your formulas. That's 1/2 mv squared is equal to mgh. Mass is the same on both of them. We can get rid of it. So we have 1/2. We have that 18.97 squared is equal to gravity, which is 10, times the height, which we do not know. Multiply this, that's 360, times 1/2 is equal to 10h. This is 180 is equal to 10h. Divide by 10 on both sides, you get 18 equals h, or 18 meters equals h. So even if it looks like you don't have enough information, for example in this one, they do not give you the mass, sometimes you can actually work your way around it. Alright, hopefully this was helpful, and I will see you tomorrow, and we'll talk more about work and doing some practice problems.